Good afternoon, everyone. We'll start in 1 to 2 minutes time. Hi, good afternoon again, everyone. Today's lectures are going to be on recursion and dynamic programming, and followed by the testing lecture. Now, the reason why we're looking at recursion and dynamic programming to begin with is that for recursion, this is normally a good way for you to go about doing a first attempt regarding any programming solution, any problem that you may encounter. Afterwards, when you do the recursive solution, you can go about optimizing it and then trying to find for the iterative solution instead. Dynamic programming is also going to show us how do we go about optimizing our programs with respect to memory, such that we make more efficient use of our memory. And later on, in particular next week when we go on to space and time complexity, we also want to see how dynamic programming plays a part in that to speed up our programs as well as optimize it even more effectively. In the second lecture that we're going to do today, which is going to be testing, this is actually going to show you guys how to go about automatically and manually testing your programs using the C++ and Windows environment. And it's going to be like a very effective way for you guys to go about like writing all your test cases in programs and what we also refer to as scripts, and then how you can go about executing them and automatically getting all your test results without having to keep on rerunning the program for each instance. So when we hit that second lecture in particular, there'll also be a small live demonstration as to how we could go about writing our scripts, as how we can go about implementing our programs to see how can we test them and so forth. So let's get started with our first lecture for today. So in existence, there is quite a number of recursive problems, and all of them basically are very similar in nature. It's just one or two small little tricks that you need to figure out when you're doing recursion, and then once you figure out these tricks, the rest of it becomes quite easy. Now, the problem when you're going with recursive problems is trying to figure out what is the trick for the recursion. And the only way you can go about figure out what this trick is and to keep on getting better at it is just to practice. So I'm circling the laser pointer here. In particular, you have to practice. That's the only way you're going to get good at this. If you don't practice, eventually you're going to come across a problem that's going to stump you very badly, and because you have that lack of experience, it's going to show that you can't solve that problem in particular. You may end up solving it, but you may take a long amount of time in order to solve it regardless. So the only way to get really good at this You just have to practice. Now, when attempting a solution for any recursive problems, there are three methods we can take. The first one is known as the bottom-up approach. The second one is known as the top-down approach. And there's a third one, which is basically a mixture of the two, which is referred to as the half and half approach. Certain problems are suited for certain approaches. And we're going to see why this is when we start doing a few examples here. In particular, you might find a problem that is more suited for the bottom-up approach because it's going to be a lot easier to implement and it's going to be a lot faster. Similarly, you might find that doing a top-down approach is going to be a lot easier and a lot faster as well. And in some cases where if you can't start from the bottom or the top, you want to realize, okay, maybe you can do half of the work in the first half and then the second half on the second half, and then you can just merge the two halves together, which is referred to as the half and half approach. Some people may just want to stick one of the approaches and just keep on going with that. That's perfectly fine. That's a matter of personal preference. It's just whichever ones that you want to learn in particular or whichever ones suit you better. Make sure that you know how to go about doing the approaches for any recursive problem. So we're going to be starting with the bottom-up approach here. And it's basically you start with a very simple case for one element in the problem. And then you keep on moving up to 2 elements, 3 elements, and so forth up to the nth element. And it watches how the patterns form between these elements in order to build your solution case by case and to form the recursive solution. The top-down approach is a little more complex than the bottom-up approach. But like I said, it depends on the certain types of problems, it may be a little more suited. When you're doing this, you need to start with the nth case and you need to divide this into sub-problems going down from n to 1. So you'll go n, n-1, n-2, all the way down to 3, 2, 1. But in doing this approach, you have to be very careful about what we refer to as overlaps between the cases. Because there may be such a matter where you have to factor in the difference, but the difference is going to be applying between the n and n-1 case. And that same difference might be going between the n-1 and n-2 case, and so forth. And it may not be the same difference, it may be a totally different difference. So you have to be very careful when doing the top-down approach to see what these overlaps are going to be. And I'm going to show you an example later on in this lecture as to what we have to look out for with regards to these. The half and half approach basically is, like its namesake says, you divide the data set in half, you work on the first half up to a designated midpoint, and then the second half down to that designated midpoint, and you merge the two solutions to form that overall solution altogether. The half and half approach is more suited towards if you don't know how to start from either end to go up to or down to the end point. So for like the bottom-up approach, like let's say you go from case 1 and then you're trying to go up to n, and somewhere in the middle you can't figure out, okay, what's really going on. Then you go from the top-down approach and you go from case n and you go n-1, n-2 and so forth, and you sit somewhere in the middle and you still can't figure out what's going on. The half and half approach is a very ideal way to go about doing this, because then you can see, okay, where do these differences start and how we can actually truncate the problem from these differences going forward to reach that midpoint. Now, there are also iterative solutions that do exist for any recursive solution. And we're going to just briefly discuss the differences between recursive and iterative here. Any recursive solution is going to be very space inefficient because what happens is when you do a recursive solution, it keeps on calling itself as its function. And each function call means that you keep on needing to allocate memory to each one of those calls. So let's say, for instance, if you had to call that function 5 times, that means you're going to have to create 5 different instances of memory. And then within the function, that means if you have any variables that need to be called, you're going to have to make 5 instances of those variables and any sub-variables and so forth. And it just keeps on compounding and goes out of control. So recursive solutions, they are very horrible when it comes to memory. But if your problem requires like a very quick solution or a very not time-intensive solution, recursive solutions actually would be the best way to approach a problem to begin with. And then once you figure out the recursive solution, you can go about solving for the iterative solution instead. In most cases, when you're trying to find for the iterative solution, the code for the iterative solution is going to be a lot more complex. It's not going to be as simple as the recursive solution. And in moving from the recursive solution to the iterative solution, you're going to have to pay attention to the patterns observed while forming the recursive solution. And then figuring out, okay, how can we implement this pattern iteratively instead? So the shortcomings for this is that recursive solutions are really good for like a first attempt at a problem, or if you're going to try and solve a problem that can be solved that doesn't require a lot of time and whatnot and so forth. And you can just solve it pretty fast, and you can use how much memory that you want to solve it. That's perfectly fine. However, if the problem requires to be solved extremely fast and you can't have a lot of memory being used, you're better off trying to find an iterative solution. When it comes to your programming interviews, don't be shy to implement a recursive solution, because that's how normally people start, with trying to find a solution and then optimizing it towards an iterative solution. So it's perfectly fine if you do a recursive solution, but once you do the recursive solution, make sure you explicitly state that, okay, this is going to be like a very quick and dirty solution, and it's not going to be very optimized, but it's going to work. And once you move from there, if your interviewer asks you, so, okay, how can you think about optimizing it, then you can move on towards trying to find an iterative solution instead, or trying to figure out how you may reduce the memory used altogether as well. Alright, so so before I move on to our examples here, are there any questions regarding any of the approaches or any of the recursive versus iterative solution discussion that we had? Alright, doesn't seem like I have any questions. So, alright, let's start with... Oh, okay, wait, we do have a question. So, recursion is basically where you have a particular problem and you attempted to write the solution, but instead of trying to write the solution outright or to find the most optimized solution, you try to figure out how you build the solution on a case-by-case basis. So, for example, like if we start with the bottom-up approach, we say, okay, what happens in case of case 1, where n is equal to 1? And we see how do we solve for n equals 1. Then we can move on, okay, what happens when n is equal to 2? So we have an instance where we have an n minus 1, so we'll have a 2 value and a 1 value inside there. And we keep on going up to case n to figure out, okay, what's going to be our solution for when we hit that nth number. That's how recursion basically works. Iteration, on the other hand, is when you actually find what's going to be the most optimized solution, and you just put a loop and you say, okay, within this loop, do this calculation, and it just keeps on repeating the calculation throughout and just produces a final answer. It doesn't involve any function calls, it just runs one thing. So the examples that we're going to be seeing here in particular is going to show which approaches are going to be better, whether it's going to be the bottom-up approach or the top-down approach. So you're going to get these examples coming up here right now. Alright, and well, like I said in the previous lectures, if you have any questions, feel free to interrupt, and I'll address them once I finish discussing whatever point I am on. Perfectly fine with me. So for our first example here, we're going to be watching the factorial example, where we have n factorial, and we expand out this function from factorial into its mathematical notation, You see that basically is n by n minus 1, n minus 2, all the way down to 3, 2, 1, and so on, right? And if we need to write a recursive solution, I mean, the first question we obviously going to ask is, how do we begin this? And which approach might be the best way to go about doing this? So, in doing this particular problem, the top-down approach is going to be the best, because we saw that for n factorial, we start at n, and we go n minus 1, n minus 2, all the way down to 1. The last case, which we're ending at in the top-down approach, this is what we refer to as our base case, or terminating condition, which is going to stop our recursion altogether. Now that we have identified the base case, the other thing that we need to identify here is going to be the recursive step. And the recursive step is going to analyze the changes between two successive cases and see how we can figure out, okay, what is going to be this constant change for any two successive cases. So, in analyzing the formula here, if we go from n minus 1 and n, and we just subtract the two, we see that the difference of these two is just going to be minus 1. And if we have n minus 2 and n minus 1, the difference is also going to be minus 1. So that difference that we always see is that n is always going to be decremented by some value of 1 until we hit our base case where n is equal to 1. In that particular instance, because n here is always decremented by 1, that means it's going to be n minus 1 for a recursive step. It's not going to be such that it's going to be such that, okay, it's just going to decrement by 1, we just have to change by 1. No, it's going to be a change with respect to n. So that's why we have n minus 1 here. Even though we have identified the recursive step here requiring n minus 1, that's just only the change part. The recursion also factors in two conditions, being that it's going to be two instances of n, which is going to be n here and n minus 1. So we need to make sure that we accommodate for this regarding the overlaps here, because we're always going to have two values of n for any recursive step that we do. Anyone confused about that? Ask your questions now. Alright, so I'm going to repeat the explanation and how you can go about doing the overlap. I'm also going to illustrate it for you guys as well, so you can actually see what I'm talking about here. So, in observing what we're doing, go back my laser pointer for the time being. So, if we consider our first step for the n factorial here, right? It means that we need to take the nth case and the n minus 1 case. That's going to be n by n minus 1. Then let's say, okay, we know it's going to be n by n minus 1, and we have that. What's going to be our second instance? And our second instance here is going to be n minus 1 by n minus 2. Alright, what's going to be our third instance? Our third instance here is going to be n minus 2 by n minus 3. And we can keep on going on until we reach, okay, what's going to be coming down to our last instances here? It'll be 3 by 2, 2 by 1. And at that point, once we hit 1 here, we basically stop because we identified that as our base case. Now, watching the recursions here, and if we try to string all of these around, we see basically our overlaps here are going to be where we have repeated instances. So we have an n minus 1 here and an n minus 1 here, which is going to be our overlaps. an n minus 2 and an n minus 2 here. If we had a 4 here, we're obviously going to have an n minus 3 here, so these cancel. And we just basically still have the same cancellations going on throughout the entire thing. We also note that in between 1 here, which was n by n minus 1, and 2, which was n minus 1 by n minus 2, is that if we watch the differences here between these two, it's always going to be a difference of minus 1. And that's like if we say n minus 1 minus n, that's going to be minus 1, and so forth as we keep on. So because n here is changing by a difference of n minus 1, that's why we have this recursion step that we need to factor in. Also, because we just observed our recursion step by step here, we basically know that, okay, we still have n here and we're going to end at 1, but also because we have this minus 1 factor here, we're also going to have to figure out, okay, we have n minus 1 being our recursive step. What's going to happen in the case where, how do we string this together? And we see that we have n here, but we have 1 here. And this 1 here, basically being our base case here, is going to be substituted with our change in factor, or a recursive step that requires this n minus 1. So we factor in all these overlaps here that we just now cancelled off to figure out, okay, how we go from n to our base case. What's going to be our change in part here that we need to figure out, being our difference between any two successive cases. And because we know n here is changing by a value of minus 1, that's going to be n minus 1 for a recursive step. So we have this n minus 1 here for a recursive step, and we just need to factor that in regarding our n case here. I know the explanation is a little bit complex, but once I start showing you, like, okay, how do we actually go about implementing the code, it might be a little bit more clear. And once we keep on doing more examples in particular, and we see how we go about doing this, it's going to be even more clear, because with recursion, it's all about practice and experience. So the key things to note is that for any two successive cases, we try to figure out what's going to be the difference. So in this particular case, our difference here was minus 1. And because it's minus 1, this is changed with respect to n. So it's going to be n minus 1 that needs to be factored in for a recursive step. When we list out each one of these cases here, and let's say we go from 1 all the way down to the n case, we see that we basically have repeats of n minus 1, n minus 2, n minus 3, and n minus 4. That's going to be our overlaps. And for every instance we have those overlaps, it doesn't really make sense for us to be going, okay, we need to multiply this over again and keep on doing it. So we just cancel them out, going all the way down to the final case, which is our base case. So we basically see that we have a case here where we start from n here and we end up ending at 1. So that basically formulates our formula for us regarding how do we go about formulating our recursive step. So we have the n minus 1 from observing the difference, and we have this n here and 1 here that we just now saw here from doing the recursion step by step. We know the 1 here is going to be our base case, which we also identified from earlier. So what are we going to do with this n here? And that n here needs to be factored in for a recursive step. So when you actually do write the code for a factorial here, our base case here is that we have 1 that we need to check for, because we're going from n minus 1, n minus 2, all the way down to 1. And because we had 1 here being our final value, we return 1 here to accommodate for this. Our recursive step is going to be that change that we now observed there, being our difference, being n minus 1, and this n here that we didn't accommodate for. That's why you get n by, and we call the function here, and we, inside the function, instead of putting n, we put n minus 1. Make sense now? Or Anything else you guys are confused about? Yes, the top-down approach is from a high number to a low number. That's basically how you identify how to use top-down approach, and it's more optimized in that particular case. So the top down is because, basically, like you said, it's because we started from a high number to a lower number. So the top down approach was being suited for that. And yeah, it's basically like from an unknown start to a known end. So that's how we went with regards to that. But basically, the main reason why we chose top down for this particular problem because we start from n and we kept on decrementing until we got down to 1. So from a high number to a lower number. When we're doing the tutorial in particular, if we reach the part with recursion and so forth, I'll show you guys step by step how does this actually operate regarding this. Right. Further questions? Right, doesn't seem like we have any further questions. Okay. So this is one way how we can go about writing our factorial example here in C++ code. We can also flip the recursive step and the base case in our implementation, and we could put the recursive step for the if statement here and have the base case being our else statement. Either way is fine. Both of them are going to do exactly the same thing. It's just a matter of how you implement it. One thing to note though is that in this case, where we had the base case here, we had n less than equal to 1. And we're observing for when we hit this condition, such that we will return 1 here. But if we flip these and we have the recursive step instead for the if and the base case for the else, the only thing that changes here is that the condition for n here is going to change from less than to more than. So once n is more than 1 here, we want to keep on calling our recursive step. And once we hit up to our value of n in particular, we're just going to be like, okay, else, just return 1, and that's it. Now, someone might ask, okay, it's n more than 1, but how do we know when we exit this out? Remember the factorial part here, we're going to call n minus 1. So n is always going to be decremented by some value of 1. So once n is no longer more than 1, meaning that n here is going to be like, n here is going to be 1 in this particular case because it's not 1 more than or equal to 1. Once n hits that value of 1 there, it's no longer more than 1. So at that point, we no longer execute the if part of the statement, we just go to the else and we return 1. So either way, if you want to put the recursive step in the if statement, or if you want to put the recursive step as the else statement, it's perfectly fine. Either way is fine. Just pay attention to the condition that you put in the if statement regarding which way you decide to implement. So I'm going to give you guys some homework, and this actually is quite some practice regarding what sort of questions you actually may get in some sort of interview. So we saw the factorial function from the top-down approach, and we also saw the implementation for the top-down approach. Your homework here is actually going to write the factorial function using the bottom-up approaches. They're going to be starting from 1 and ending with n. And to add things a little more tricky, I want you guys to also go about, write this on the slide for you, an extra pointer. Write both versions of C++ code with recursive step in if statement. Oops, one. And in else statement. So this is actually going to be your homework for you to actually attempt and practice regarding this. This is also a sort of type of interview question that you may also encounter for any programming. And it's basically designed to test, okay, you may know one approach. What happens if you wanted to implement it in the other way instead? So they want to see how do you change your thinking to implement it for a different approach altogether. One thing I want to tell you guys up front here is that any homework that I decide to give you on these slides here, they count towards something throughout the entire course. I'm not going to tell you what, but you'll figure it out pretty soon, especially within the next 2 to 3 weeks. Why do they count? And the reason why you're getting on the slides here is actually to get an early start regarding. Alright, so for our second recursion example here, we're going to start here where we have any two positive integers a and b, where a is always going to be less than b. We need to find the sum of the squared integers starting at a and ending at b. So remember, a is always less than b, so we start with a here being our least value, and we square it. Then we go a plus 1, square that, add that result, plus a plus 2 squared, add that result, plus, and we keep on going all the way up to b squared. So for this particular case, I'm going to submit a poll here. Which approach is going to be the best for this situation? No, the answers on the next slide. But don't cheat. Let's see how you guys go about doing it. I'm going to give you guys an additional 30 seconds for any last minute votes. Right, closing in 3, 2, 1. Right, our poll is ended. So basically, we saw that the majority of you guys, being more than 50% of who voted, said that the bottom-up approach would be the best. And we still had some people who was thinking, okay, about like 20-something% said top-down, and that's it. So the bottom-up approach, 53% of you guys said bottom-up will be appropriate. Half and half was 28, and top-down was 18, and of course nobody would choose none of the above because there's only 3 approaches. So the bottom-up approach, it will be the most strategical approach to use here because we're starting from a less value and we're going up to a greater value. Half and half can also work here as well, but half and half you're going to encounter a lot more difficulty because we don't know what's going to be the midpoint in particular. We can say, okay, we can add a and b and divide it by 2 and hope that we do find the midpoint, and at some point we may encounter it, but we're dealing with integers, not decimals. So what happens if we get an odd number, we add a and b and we divide it by 2? How do we determine what's going to be our midpoint in that? Do we round down or do we round up? All those things you have to consider when you're thinking about doing the half and half approach. The top-down approach can also work here, but it's also going to be like our previous problem where you have to write it in reverse, and it's going to be a little bit different with the implementation. So for our illustrations here, we're going to be using the most strategical approach, which is going to be our bottom-up approach. So because we're going to be ending at B using the bottom-up approach, this is actually going to be our base case. However, when we compare to our factorial that we just now observed, we also observed, okay, what was going to be our changing conditions and so forth, and we also saw that the last thing was that we returned 1. But in this particular case, we're not going to be returning B at the end, even if we do observe those patterns. What we need to find out is what's going to be our overall sum, and we need to return this as our result. So how do we formulate our recursive step in this particular case? And we go back to the formula to observe, okay, how do we formulate this recursive step? So we do the same steps like before, that we see the difference between a plus 1 and a here is 1. And then from a plus 2 to a plus 1 is also going to be 1. But a here is always going to be changing up to a value of 1 up to b. So because we see this change here, that means if a is changing by a value of positive 1, that means it's going to be a plus 1 that is required to factor into our recursive step. But we also need to keep this with a track to b to make sure that we don't exceed this value. And we need to make sure that in doing the recursive step here, that we make sure that once we arrive at b, we stop doing any further calculations because we actually hit the uppermost limit or great value here, and we just produce the result immediately at this point in time. So in writing this in C++, we need to make sure that once a here is going to be greater than b, we return our result as anticipated. So this will be our base case, because we don't want a going greater than b because a needs to be less than b as specified in our formula. Once a goes greater than b, we return that result immediately, we don't do any further calculation. Our recursive step here is that we need to make sure that we square the value of a here, a by a, and we put this into a temporary register or a temporary variable, which is going to be result. We have plus equal here. The reason why we have plus equal is that we need to keep on adding this result and storing it at each recursive step. So like for step 1, we would have a squared, highlight this, right. So this way we have a squared in 1 and this will be end result. Now we go to step 2, we'll be doing a plus 1 squared. And this also needs to store in results. But we can't overwrite this because we have to factor in this addition. So we need to make sure that we add the two together. Then when we go here, this here is going to be step 3. We need to make sure we add that as well into result. So that's why we have plus equal here to keep on summing the results and storing it in on our register or variable here named result. Finally, for the recursive step, we need to make sure that we call back the function, but we also need to make sure that something changes here so that we can make sure that our base case will actually process when required. So we go a plus 1 here. We still call b as required because our function here requires 2 inputs, a and b. B doesn't change here. And in our recursion, we need to make sure that this result here is added in order to make sure that it keeps track of it. If you do not add that, when you return, it's going to be the last step. So it will end up just being b squared because you are no longer keeping track of this result at every recursive step. Alright. Anything to ask in particular about the sum of squares approach that confused you? Oh yeah, sure. So in the recursive step, remember that in our particular cases here, with this, is that, okay, we need to know, okay, what's going to be our changing factor to begin with. So if we had a plus 1 here and a here, even though they're squared, but you want to ignore the squares here because we just consider how a is changing in brackets. A plus 1 and a, if you minus 2, you want to get 1. Same thing if you go a plus 2 and a plus 1, it's just going to be 1 here. So we know a here is always changed by a value of 1. Remember, a here is always going to be less than b, because a is the lesser value, b is the greater value. So because we know a here is always changed by a value of 1, that means the recursive step will have a plus 1. And keeping track of how do we go about doing this, that's why I'm going to go back to the code here. I'm going to show you guys how we went about formulating. So the base case here, which is very obvious, once a goes greater than b, you need to return the result immediately. You don't want a going greater than b because a needs less than b. With the result here, we have plus equal to a by a. What is a by a? Is just basically a squared, right? And for every instance of the recursion, in each recursive step, we need to make sure that we store that result and add it into our result from the previous recursion step. So when we start our recursion here in particular, we're going to be starting with a squared. That's step 1 here. And a squared will be stored in the result. When we go to step 2, because we have a plus 1 here, so we need to make sure we keep on changing until we hit up to the value of b. When we go a plus 1 here and we square this, remember, we now have to make sure that we accommodate for the a squared here and the a plus 1. Because we're now at the second step. And accommodating for those, that's why we need to add them together here. So the result of the a plus 1 squared needs to be added because of addition here to the result of a squared from before. So that's why we have our plus equal here. Keep on keeping track of the results as we go up in values of a for each recursive. In order to make sure that we have our recursive step complete here, remember we started at a and we're going up to a value of b. So that's why we have a plus 1 here, which we formulated earlier. B here remains the same because that's going to be our uppermost limit. For the recursion to work and keep track of the results, we need to add the result here when we're doing our recursive step with the return statement. If we don't add this result here, when we return results, all it's just going to return is just going to be b squared. Now I understand that part in particular. It may be a little bit tricky to wrap your mind around it, but once you actually implement this code in practice, and like I said, if we get to it in the tutorial, and you actually start observing it step by step how the code operates, you will see why it is important that we need to add this result. If we don't add that, we're not going to get our results as intended. We'll get a completely different answer. All right, any further questions at this point? Alright, doesn't seem like we have any further questions. So I'm just going to reiterate one point that I made at the start of this lecture. The only way to understand recursion is actually doing practice. So you're going to have to keep on practicing and practicing until you actually formulate your methods to do recursion and so forth. And then once you start formulating your methods and seeing, okay, what's going to be our key differences here for each one of these problems, that's the only way you're going to understand recursion. You actually do have to practice to keep on doing it. Now, like I said, in some cases there may be one or two parts that doesn't clearly be explained here on the slides. But when we do go into the tutorials and you actually start seeing live why these steps are important, it's going to be a lot more clearer as to why we do particular things. So I know right now certain things might still be a little bit unclear, but when we go into the Wednesday session for our tutorial, I'm going to address these in particular, and you're going to see why it is that these particular things are important regarding our recursive steps here. Alright, so for your second homework here, I want to ask you guys to go about rewriting solutions for both example 1 and 2 to use pointers instead of the inputs to the functions. And you cannot use the address operator, being the and sign, while you do it. This is also another interview question that you go. If you want to go and practice in particular, let's see if I have a link for a resource here so I can give you it one time. it's nice to actually go about actually implementing these things in particular, and then trying to go about trying to observe them step by step in your compiler to go about observing how the changes actually do occur. So I'm looking for a version problem, something nice and simple, because there's a lot of complex recursions. Okay, so I can't find the simple link at this point in time. Once I do find it, I will post it up on the forum for you guys to see, okay, where you can go about practicing. There are no particular conditions where a recursive method will work exclusively as opposed to an iterative method. Recursive methods are easier to implement. That's the only advantage it has. It's a lot easier to implement, it's a lot less line of code, and it's like a very quick and dirty approach. The disadvantage is that it uses quite a lot of memory. So if you don't require, if you're not limited on memory, sorry, a recursive situation will be better as a first step in finding the optimal solution afterwards. If you are very constrained on memory, however, you're going to have to try and solve for that optimal solution immediately. Right, so I'm writing here on the slide so that way I do remember to look for this link. Practice link. Problems. And I will look for that practice link and I'm going to post it on the forum for you later on once I do find it. Alright, yeah, so going back to the second homework here. So you have the example code here for examples 1 and 2. Instead of using direct integers in our particular case, I want you guys to implement these functions using integer pointers instead for the inputs. And you cannot use that address operator, being the and sign, whatsoever within your code. You have to use the pointers as is within the code. You're free to dereference them and so forth, but you cannot use this and operator. This is actually going to be your second homework for you to attempt. And like I said, this is also a type of interview question that you may also face in the programming interview. Alright, so that's basically the end of us discussing recursion at this point. Like I said, the practice for recursion was going to come a little bit later on with regards to actually observing it step by step how the recursion actually works. And that's going to be in our tutorial session for Wednesday. I believe that's going to be the first hour. Yeah, that's the first hour on Wednesday. So we're going to go through that in particular as well. So for dynamic programming and memorization, not to be confused with memorization, there's no R here. We're going to be discussing this at this point onwards within our lecture. And a lot of people think that dynamic program problems are very scary, and it's just really because they lack the practice. Now, in order to go about doing dynamic programming, you have to use a recursive algorithm or recursive solution first and find these overlaps, and then we do something referred to as caching. So with caching is basically like a temporary storage for any of these. And we had a very simple cache here that we just don't use regards to our result. It tracked our result for every recursive step. That acted as a temporary memory location or temporary memory variable that kept on storing the result of each step of the recursion until we got up to our final result. So that's where you actually saw it in example 2 here. It is also possible that in any iterative solution, you can cache previous work as well. And it's the same concept. You just have some memory variable that just keeps on acts as temporary storage, and it just keeps track of something, or it may be used as a lookup later on, instead of having to repeat an entire calculation throughout a function. So our third example here is going to be based on seeing the dynamic programming and the memorization concepts. So some people may actually know what the Fibonacci numbers are already. Forgive me, the other people who don't, I'm going to have to actually explain this to them. So the Fibonacci numbers is basically what we refer to as a Fibonacci sequence. So the sum of each number, such that the sum of each number of the two preceding ones is going to be starting from 0 and 1. So the first Fibonacci number is going to be 0, the second Fibonacci is going to be 1, and the Fibonacci formula is that f of n here is going to be equal to f of n minus 1 plus f of n minus 2. So we can observe this by using any two pairs of values. So if we have, in this particular case, this here being f of n, this is f of n minus 1, this is f of n minus 2, and we plug that into our formula here. We see that we have 1 here equal to 1 plus 0, 1 equals to 1, so that's going to be true. Let's use this here as our result. This is going to be f of n, this is f of n minus 1, and this one here is f of n minus 2. So then we see 144 here is equal to 89 plus 55. And we'll see here this is 144 equal to 144. So it's basically just a pattern that we observe here regarding numbers to make sure that we can have a track of them regardless throughout the entire sequence. That's basically just what the Fibonacci sequence. Just trying to figure out, okay, we have a higher number here. What's going to be the sum of two previous numbers? They can give us this higher number. And if we go down here, okay, for this particular number here being 89, what's going to be the sum of the two previous numbers here that could give us 89? And so forth as we keep on going until we hit 0. So the recursive solution for Fibonacci actually looks like this. Because once we have 0, we're just going to return 0. Once we have 1, we return 1. Otherwise, we're going to just have I minus 1 plus I minus 2. And the reason why we have I minus 1 here and I minus 2 here just matches our formula for f of n minus 1 plus f of n minus 2. So this part here is actually going to be our recursive step. Our base cases here would be f of 0 and f of 1. So once we have 0, we return 0. Once we have 1, we return 1. So just to illustrate this, so this is our base cases here, and this here is our recursive step. So yes, the first instance that you do observe here, and someone might ask this, is that why do we have more than one base case? And that's also quite popular in recursions. It is possible to have more than one base case in a recursion. The base case is just how do we stop the recursion from happening. So it's very possible to have more than one base case. It's also possible to have more than one recursive step, but that's a little bit more complex. And we're not really going to be going into much detail on this. In an interview, that type of question normally is not asked. That's like if you're going for like a really high level or high position, they may ask you that sort of thing. But for now, we don't need to be concerned about having multiple recursive steps. We just need to be concerned about, okay, we can have multiple base cases, stop our recursion altogether. So for Fibonacci here, we have the code, but actually let's observe this by drawing what we refer to as a recursion tree to visually observe what actually does happen when we actually do this Fibonacci sequence. So if we started with I equals 5, so let's just write this here. And we know that f of n is equal to f of n minus 1 plus f of n minus 2. So when we add 5 here, that means we're going to be f of 5 is equal to f of 4 plus f of 3. So for fib of 5 here, that means we need to have a fib of 4 and a fib of 3. Now, for fib of 4 here, that also means that we're going to have fib of 3 and fib of 2. For fib of 3 here, we need fib of 2 and fib of 1. And for fib of 2, we have fib of 1 and fib of 0. 1 and 0 here being our base case. Similarly, on the right-hand side of the tree, we had fib of 3 here. So this fib of 3 will go fib of 2 and fib of 1. Once we hit fib of 1, we basically end because that's the base case. And fib of 2 here, we have fib of 1 and fib of 0 as well. So observe here within the trees here, that all the leaves being that the end points of the tree, from going from the top to the bottom, all end at fib of 1 and fib of 0. And those basically signify the base cases here that we just now have. Where I is equal to 1, we return 1. If I is equal to 0, return 0. Those basically are our base cases. Now, if we start counting how many nodes we have in the tree here, being each node being represented as a function call, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? And for every node that we have here, we have 2 children regarding the nodes. So like fib of 5 has fib of 4 and fib of 3 here. And each node has 2 branches, no matter what, until we hit fib of 1 and fib of 0. If this keeps on expanding, so instead of 5, if we go up to some huge number of n, we will always have 2 of n nodes regarding this problem. Now, keep in mind that when we have 2 of n nodes here, we want to see why this 2 of n is going to be important. So if we graph 2 of n here to see what happens, we see, okay, yeah, it starts off pretty nice, everything is nice and dandy and so forth, and then it extrapolates here and it gets very horrible, tends towards infinity. And this is not good at all. This is like extremely horrible. It means it's going to take a lot longer for us to try and solve for larger values of n, and it's going to just compound and go even worse. So this is horrible for scaling. Extremely horrible. 2 of n is like one of the worst possible outcomes regarding this. And even though it is the worst possible outcome, or one of the worst possible outcomes that you can actually achieve, there are ways to optimize this. So let's go back to our recursion tree and think about, okay, how can we optimize this? So in observing the tree here, we see that there are repeated nodes, because we have a fib of 3 here, we have a fib of 2 here, and so forth, and we have fib of 1 and fib of 0 repeated all over throughout the entire thing. But fib of 1 and fib of 0 here are our base cases, and that's just basically return 1 and 0. The calculations for fib of 3 and fib of 2 and fib of 4, we basically see that those calculations need to be repeated each time for a Fibonacci series. And the question here is that if we do calculate the value of fib of 4 here, and then we go on and we calculate the value of fib of 3 here, do we really need to recalculate the value of fib of 3 here as well? Because when we actually watch the sequence of operations, we start with fib of 5 here, and we have fib of 4 and fib of 3. But at this point, we already calculated fib of 3. We need to recalculate fib of 3 here already, but we already have the value of fib of 3 here to begin with. So instead of having to do an entire recalculation, we should probably just grab this value here and just replace it at this point, instead of having to do a full recalculation. So this is where memorization comes into play. If the calculation was done before, we don't need to recalculate it. We can just store that value somewhere and just recall that value and use it later on. And that temporary storage is what we refer to as caching or a result. So if we tweak our code here, it's possible to actually use memorization to go about doing this. Now, I know the code here looks a little bit complex, and We will come back to this code in later lectures when we start learning new concepts, in particular as to what this code actually can do. In particular, this might be one of the first times you actually start seeing the use of the new keyword here for memory management plus the passwords. Now, if you're feeling brave, I'm not going to stop you. You actually can implement this code and go about running it in your compiler, and you can step by step it, or you can put a breakpoint, watch it, and see how actually it operates step by step and keeps track of each previous calculation as it keeps on going. And the code for keeping track of this is going to be this if statement here. This code here is going to be caching all previous results that were already calculated, and then it's going to be also responsible for its usage later on instead of doing a full recalculation. So once we have these calculations actually occurring from beforehand, and we actually have caches here, we no longer need to go and do one set of repeated calculations. We can now just use the cache values here, and we can just go about doing our calculations throughout then. So instead of having the tree branches left and right, we only have one branch to the right, and then we have all the repeated branches here on the left, but we have our cache values here being used later on throughout the entire calculation. So there are less repeated calculations or less repeated computations as a result of caching values that were already calculated before. Alright, so any particular questions at this point in time in regards to the concept of memorization? You should try to plot a recursion tree anytime you're attempting any recursion problem, because it helps you spot the patterns a lot easier because it is a visual approach. Some people may not opt to use it because they can formulate the recursion steps and so forth just from watching the formula itself, but it is always a good idea to do a recursion tree if you are getting stuck, so that way you can visually see where do these repeats occur or where do the recursions occur, how do they compound with one another and so forth. It helps quite a lot in this. So if you're more comfortable using the recursion tree, by all means go ahead and use it. You don't have to, but it is a very helpful tool. Fibonacci numbers is just basically an example here to go about showing how we can actually store results instead of doing repeated calculation. There isn't really a practical use for Fibonacci numbers as far as I know. It's just basically like a fancy mathematical computation or pattern in numbers that you just basically observe. But in using this, it shows the important concept of memorization. So like for instance, an interview question could come and be like, okay, can you show me an instance where memorization is important? And you could refer back to this Fibonacci example to actually explain, okay, we have repeated computations happening, we don't need to keep on doing these computations all the time. We can just store the results and just call it back later on. All right, any further questions? Yeah, simply memorization is just basically a way for you to cache results from previous calculations. And then recalling those results when required. Alright, so doesn't seem like we have any further questions. So, well. So, in observing the recursive tree that we just saw here, memorization visually makes sure that our recursive tree goes less wide instead. And this is because of using the cache values to reduce the amount of time required to compute the overall result, because we no longer have to do any repeated calculations. We just store the results and then report them backward when required. In using memorization, this cache or the storage of values is very small when it comes to memory. And especially when you start dealing with large amounts of data, memorization is quite important because it reduces overall amount of memory that your program is required to use, as well as it also helps with speeding up your program, because it's a lot easier and a lot faster to retrieve a value than it is to actually go and compute a value. Alright, that brings us to the end of our first lecture. And basically what we saw here is that we saw how recursion basically operates and how it works. So you can go about formulating or base cases on recursive steps. In some instances that if you do not see how the recursion works, like I said, once we hit recursion in the tutorial and we physically see how it operates using the compiler and step by step, you'll understand why certain things are done in the recursive steps and how they actually play an important role in order to get to the final value. We also watched the concept of memorization here with respect to dynamic programming and how it is that it reduces your computational workload in terms of execution speed, as well as the amount of memory that your program uses. In particular, we saw that the use of any cache that can be used to store values from previous work, and then it can be recalled later on when required, speeds up our program, as well as uses overall less memory throughout the entire execution of your program. And this is possible because of our cache or temporary memory that we implement within our program. Alright, so there weren't any further questions at this point in time, so let's move on to our second lecture for today. Keep my ink annotations.